Welcome students to our new session. In this session we will discuss about basics of transducer interfacing, then some techniques which are related to grounding and shielding, because this will help us in to removing noise and better data acquisition. So let's start. So today we'll discuss in this flow, first of all we'll discuss about transducer interfacing, that is unipolar bipolar interfacing with the operational amplifiers and signal conditioning circuit. Then we will discuss what is the best sampling rate while we are doing data acquisition. Third thing which is important is signal isolation. When we join two different systems, then signal isolation is very important. So we will discuss that also. And in the end of the session, we will discuss two main things about the data acquisition and interfacing, and those are grounding and shielding. So let's start with the transducer interfacing. So whenever we have important thing, what we comes in our mind, that how to connect that transducer with the signal conditioning circuit. And the most common thing about this circuit is that these are based on either bridge circuits or they are based on the voltage divider circuit. So let's start with the first one, that is when transducer is used in a voltage divider circuit, which is also called a half bridge. So in this circuit you can see here is the sensor, this one is the sensor, and these kind of circuits are very useful when the transducer is a resistive one. So it is exclusively for examples are LDR. So when we have light dependent resistor, or I can say when we have RTD, that is also a resistive transducer, or any other resistive transducer like strain gauge, something like that. So the first option with us is to connect that transducer into a resistive network where we have a known series resistance, which is known as, let's say, RS, and the transducer, which is known as RT, and we can connect them in series. On one side of it we can connect 5 volt or excitation voltage, whatever it is, maybe 10 volt, but usually we keep it 5 volt so that the next circuit can easily handle this. So we'll connect among 5 volt and ground. On this side we have ground, and where the junction of RS and RT is, there we use one pin to connect with the signal conditioning circuit. So signal conditioning circuit is connected with one pin at ground and another pin at the junction of these two resistors. So I'll show you one example in the next slide. In most of the modules which we are using these days with Arduino or Raspberry Pi, they people are using these kind of voltage divider circuits or bridges. So the next option is with us when we are using transducer in the bridge, and this is the most common, most popular one. The reason being, this is the most accurate among all of these configurations. But the first one is economical, the half bridge configuration. This one is economical. So advantage of the first configuration is economical. So because we have to use only one resistance in addition to the sensor what we have, so this is economical. But the second one is most popular because in the Wheatstone bridge we have many other advantages, like when we can do the amplification also with the arm ratio. Although we have op-amp, but we can manage some kind of arm ratio and we can manipulate with the amplification of this bridge. So in the second case you can see we have the bridge, and in the bridge here is the transducer. So again, one side of the output is connected to the ground, and other side what we are getting from the bridge is directly fed to the operational amplifier. So it is non-inverting amplifier configuration. Whatever we are getting signal from the bridge, that signal is being amplified, and other advantages of op-amp has been being used in this circuit. Now coming to the third option. In the third option, you have to look careful that we are going to connect the output of the bridge as bipolar input to the instrumentation amplifier. Now what is bipolar input? It means whatever the output is coming from the bridge, those two pins are directly fed to the op-amp or instrumentation amplifier. One is connected at positive, that is non-inverting terminal, and another output pin is connected with the inverting terminal. In the previous case, we have connected one pin as ground, so we call it as one pin input, that is one pin of the output is connected to the ground. Here one pin of the bridge, that is why I am saying output. These two pins are output pins, so none of the pin is grounded, only the excitation junction is grounded. Okay, so we will see advantages of three different configuration in the next coming slides that we have discussed. Let's suppose in this instead of here MCU, if I connect an op-amp and one side of op-amp is connected to this pin. Let me try here. Let's say this is positive terminal, negative terminal, negative terminal. Further we are using some resistance for an inverting input. So what we can do, we can connect this output to inverting terminal and this pin can be connected to the ground. Then in that case we can say this is single-ended input or a unipolar circuit like here. Now what is bipolar? Bipolar is like what we have discussed just in the previous slide, when we are connecting in the bridge or when we directly giving output of a transducer to an op-amp's two pins like this. So if we have a third pin, there are many other pins to that transducer, and some other pin is being used for ground and some other pin is used for VCC, let's say, and there are two exclusive pins for the output, and those two exclusive pins are directly connected to the operational amplifiers, inverting pin and non-inverting pin. Then we say this is a bipolar configuration. I hope it is clear to you. Now in the market we have available such kind of transmitters rather than transducers. In the market they are also known as transmitters. The reason being transmitter I will tell you later, but first discuss unipolar and bipolar. So there is one company which provides different transmitters to be connected in the line, either unipolar configuration or in the bipolar configuration. So transmitter means when the transducer itself has a capability of connecting with field bus or 4 to 20 milliampere connecting line, telemetry line, then that is called transmitter rather than transducer. So till now what we have discussed is transducer interfacing is very important, since most of the time we come across resistive transducer, so we have discussed those examples. But instead of, if we have capacitive based transducer or inductive based transducer, even then we can go for bridges. You must have read about bridges which are based upon capacitive, like D-Shorty bridge, and inductive bridge in which we control the inductance of the circuit. So it depends upon the transducer. If we have a resistive transducer, we will use Wheatstone bridge. If we have capacitive, then we can use D-Shorty and other capacitive bridges. And if we have inductance as a variable for the physical phenomena, then we can use inductive based bridges like Wien bridges or Hess bridges. Okay, next important thing is sampling rate. That is, when we have connected the transducer for data acquisition, what is the sampling rate? Now why it is important and what is sampling rate? I hope you have studied already about it, but let's revise something about sampling rate. So sampling rate is speed at which data acquisition device के अंदर जो data acquisition device ADDC, ADC means A to D converter. So analog to digital converter is taking samples from the analog signal and converting it into a digital one. So the speed at which that ADC works is called sampling rate. If I give you one example, let's say this is an analog signal. Now A to D of that device is sampling, let's say I have deliberately made this signal non-synchronized or unsymmetrical, that it is not symmetrical about zero axis, it has some DC level. So this is the first sample, let's say. After 1 microsecond it takes the second sample, after another 1 microsecond, let's say it takes the third sample. So that is the samples it had taken. So built in it has a quality to hold that level in terms of sample and hold circuit, and that is why it is converting only that particular sampled value within the conversion time. So sampling rate means after how much time it is sampling the next sample. So in this case I have taken it as 1 microsecond. So it means in 1 second it can sample up to 10 raised to power 6, that is 1 upon 1 micro. Okay, so it will become 10 raised to power 6. So these are the number of samples that it can take in 1 second. So that is the sampling rate. But these are the most common sampling rate, either 1 mega samples per second or it's 2 mega samples per second. So these are the common sampling rates what we are considering in real-time data acquisition systems. You are well aware about Nyquist theorem. Although this theorem says that to acquire accurately or to reconstruct the signal accurately, the sampling rate must be 2 times the highest frequency. Now this Nyquist theorem is giving us the minimum sampling time, that is 2 times. But actually when we do some experiments, and this is the example of one experiment, we have taken one sine wave which is of 1 kilohertz, and as per Nyquist theorem we can take the sample at 2 kilohertz as written here. So once we taken the sample at 2 kilohertz, which is double the time of the signal's frequency, that is 1 kilohertz, you can see the blue one is, it's mentioned here, the blue one is 2 kilohertz. So you can see it's completely triangular wave, not a sine wave. So it means we are missing some information even at the double frequency of the signal. And when we take 10 times 10 kilohertz, then it a little bit tries to convert into a somewhat sine wave, although it is not exactly sine wave, but it try to give us a bit real information toward that signal is not a triangular wave. So if we increase more, let's say about 40 kilohertz, maybe our sine wave become more smoother at the edges. So the sampling rate is very important. It may totally change how the signal is look like when we are acquiring it in terms of digitizing. That is, after A to D, it will drastically change the behavior of the system. So sampling rate is very important once we are interfacing the signal. Next important thing is signal isolation. Now, what is isolation and why this is important? Isolation means when we have a circuit A and we want to give that information to circuit B. Okay. So we want to isolate the information available in this side from this side. The reason being, it may be possible that the A-type circuit is working at, let's say, 5 volt and the B circuit is working at 12 volt. So, or maybe at 24 volt, and moreover it has some inductive circuit which is producing some high frequency signal. So those high frequency signal can change the behavior of this signal. So we want to isolate this signal. So how we can do that? So we will discuss in this particular example. Here the main application or the main methodology given to us is that is through optical method. That is, we should use some optical medium to transmit signal from A to B circuit rather than connecting with wires. Okay, we are using optical medium. So optical medium, what could it be? It could be an LED which generates the light as far as there is a digital high, it will glow. When there is a digital low, it will go down, off. So this digital information can be transmitted through an LED, and on the other side we have a phototransistor which will capture the high and low signal. So for digital it is very easy. Once we acquire the data, digitize using A to D, and after ADC we can isolate the signal towards the next stage, sending through that signal via LED and phototransistor, and in combination this is known as optical coupling or signal isolation using optical medium. Another important thing is about this, when we use isolation, we are breaking the ground loops. Now what do you mean by breaking the ground loops? It means the circuit on this side has its own ground and circuit on the other side had its own ground. So they have different grounding signals, and that is why it is called isolation. We will discuss later on what are the advantages of doing this grounding signal different, and there are sometimes cases when we need to combine the ground. So when we discuss grounding techniques, we will discuss this phenomena, that is when it is better to have different ground and when it is good to have a common ground signal between A and B. So this is another example of signal isolation that I have already told you, that let's say there is a circuit A, circuit B, and to avoid any kind of noise between these two circuits, we have to go for signal isolation, and sometimes it is also called power isolation. So when we use the term power isolation, it means the circuit A has its own power source including ground, circuit B has its own power source including ground. So there are different symbols have been used for the ground to explain that there is a power isolation also in addition to signal isolation. That is, the circuits are working on different power supplies, so there is no direct connection between their powers also. Now what are the advantages of these kind of circuits? The first advantage is protection from the high voltage. So if in any of the circuits there is a high voltage due to switching on, switching off, and we want to protect our circuit from that, then there is a power isolation. In most of the digital circuits, when we are connecting high voltage transducer and we are interfacing with the laptops, we are using these kind of circuits. So we are using two things. We are using signal isolation, so that signal should not have any kind of noise, and we are also avoiding direct power connection with the device B and circuit A. So if circuit A is working on, let's say, 230 volt, and we want to connect that relay directly to the laptop or some other sensitive circuit, then we need to have a different power supplies, and we need to have isolate between these two circuits. So that isolation is being fed to some isolation circuits, and we have to take care that there's isolation for the signal as well as for the power. Okay, that was the first advantage. The second advantage is with the level transition. That is when we are moving from 230 volt to, let's say, 5 volt, or vice versa, from 5 volt to we are going to 24 volt. Then there is a change in the level. Okay, so that change in level can be easily operated without any noise, without any surge, using this signal isolation or power isolation. And third, which is important as far as signal is concerned, that is noise elimination. So if there is any noise, we can easily remove it because we are giving only high or low towards this side. Okay, so if even there is a noise, something like this, okay, the other side of signal, this side of the circuit, is only sensitive to a threshold. That is when this value crosses some level of, let's say, TTL logic, for example. So when this side of circuit crosses a particular level, let's say 2 volt, for this side of circuit it will be a high, level 1. If it is below 2 volt, it is logic 0. Okay, so whenever we are giving A to D after this high voltage potentiometer or transducer, then there will be op-amp, then finally there will be an ADC. I've already told you. So after the ADC, when we are giving the signal to this side, it is only a digital signal. Okay, so any noise in the digital signal can be easily removed using isolation. Uh, 3-terminal combination like this. In the switch plug, this kind of plugs have been there. So the use of these 3 terminal is, one is for line, one is for neutral, and the third one, which has a bit bigger size, that is for the earth. Now practically this earth pin should be connected to the actual ground, which I have already told you it's connected through a conductor made of copper or aluminium and buried into the earth, actually around 10 feet depth. So that is the actual ground. Okay, and we call it as earthing. So when we have such kind of symbol, it means we have earth grounded and our power supply is connected to that ground, and our ground is connected to our circuit's ground. So that is the absolute ground or star ground. Star connection means there are 3 different types of grounds and they all are connected to each other. Okay, so that is the different configuration. First is current return configuration. Second is when current return configuration is connected to the main supplies ground, then main supply ground is further connected to the earth. That is the third condition, and this condition is actually similar to this one. That is, they have individual grounds, but individual grounds are further connected to the main power supply. If main power supply is further connected to earth, that is well and good. So these are some of the configuration what we use in signal conditioning and data acquisition, and a transducer must be connected in such a circuit which should be at least grounded with the power supply. It should not be the floating circuit like the first example. We'll see what are the disadvantages of these circuits in the next coming slide. Now, if our circuit will be of floating ground, like in this case, it is very easy to understand what is happening here. What is happening here? Let me elaborate. This is an apparatus, a device whose body is maybe a conductive one because it is made of metal cabinet. So once we have made a circuit whose ground is naturally connected to the cabinet, and this side of power supply is not been connected to the ground, actual earth ground, the third pin ground. Okay, it's not earth, properly earth. Then what will happen? the circuit will work properly, no issue. But its own reference, let write down reference, is not at the absolute 0 volt, which is equal to the earth ground. Okay, so when this metal body is not at actually 0 volt, not at the absolute 0 volt, but it has its own reference, so then the current may flow through the human body and human can get a proper shock. It depends upon the shock, that how much voltage the circuit have or the current the circuit have. Okay, so it's very dangerous when we have very high voltage circuits or high current circuits without any absolute earth. So in this diagram it is explained that what is the best way, that when we have the device, if you have its own circuit, that is current return is there, very good, negative and positive are connected properly in the circuit will work. But when you forget to connect this reference to the absolute reference, there may are many chances of floating ground and other chances of human got shocked, electric shock, and there are other disadvantages of current surge and high voltage and other noises. So it is always better to properly ground your interfacing circuit with the absolute ground. This is a that is the example I have already explained you. The reason having the third pin in our power sockets. So in most of the buildings it is required as per IEEE standards. So you can even go for further readings. You can go and search for IEEE standard for earthing. This is very important to search earth ground. It will help you when you make your own capstone projects. Okay, that is the star connection that I was talking about. That is, sometimes it is possible. It's not always possible, but sometimes it is possible to connect all the grounds, that is analog ground, digital circuit ground, to the main earth ground with each other. Okay, in many of the circuits, sometimes when we draw this kind of symbol, it means it is the ground of circuit, it is not absolute ground. Absolute ground is always referred like this. So when you have three lines, it means you have earth ground. When you have symbol in the circuit like this, it means you have connected ground with the main power supply, but it is not sure that power supply is further connected to earth or not. When you are sure that it is connected with the earth supply, then you can use this symbol that our circuit is properly earth grounded. Okay, so that is the philosophy behind three types of grounds: analog ground, digital ground, and absolute ground or earth ground. Okay, coming to the next thing is electrostatic discharge. This is very important when we are handling some very sensitive circuits, especially memories or CMOS based circuits. They are very sensitive to electrostatic discharge. Since we people are using now polyester kind of cloths, and we are using plastic chairs, and when we are keep on sitting or due to rubbing of our clothes with the other sitting material, there is always a possibility that we are carrying a static charge. I can guess that some of you have may come across some situation that when they sit in the, especially in the winters, when we people are wearing woolen clothes, and when we are getting outside from our car, sometime you come across sudden electrostatic discharge when you touch the body of the car or some other situation. The reason being that is we are wearing woolen clothes, and when we are rubbing our body, or those cloths are being rubbed by uh, the seats or the other plastics, so there is a electrostatic charge on our body. Okay, and whenever we touch a metallic thing, suddenly that that charge get discharged, or there is a small spark for a very minute time. Okay, so that is due to electrostatic discharge, and that small discharge may be damaging for very sensitive kind of sensors, transducers, circuits, and even memories. If you have come across some kind of sensitive devices or circuits, you must seen that few of the devices are wrapped in yellow kind of envelopes, or there is a very large sticker of yellow color, and on that yellow color sticker there is a symbol like this. So that yellow sticker pasted on that envelope, it means the circuit board inside that envelope is very sensitive to electrostatic discharge. So be careful whenever you are handling those kind of ICs, those kind of batteries, memories, or the circuits. Okay, so let's see a bit about why it is important to having these kind of electrostatic discharge, very important, and how can we manage those kind of electrostatic discharge, and how can we save those ultra sensitive devices from being damaged to this electrostatic discharge. For that, what we are using? Grounded mats. Grounded mats means, like in this example, this blue color mat is actually, you can see, connected to the third pin of, see, look carefully, third pin of the power supply. This is absolute ground or earth ground. So we have one pin, it is easily pinned in the mat, and that pin is further connected to the third pin of the power supply, which is actually earth grounded. So now our mat is properly earth. So we will, and before handling to this device, which is very sensitive, we have to wrap around a wrist strap. So like in this example, on the wrist, that person is wearing a wrist wrap. This wrist strap is also further connected to this mat. So it means now our body is also properly earth grounded. So before handling to such kind of sensitive equipment, devices, sensors, transducers or ICs, we have to have these kind of protective equipments with us. Only then we can go for the further interfacing or handling of these devices. So I hope before today's lecture you are not so much concerned with the grounding and earthing, and now you can imagine how much important it is. Okay, so be careful when we are handling very sensitive devices, either they are memories, ICs or other devices. So be careful while you are handling, especially when there is a symbol like this. So it means the device is very sensitive to electrostatic discharge. So now coming to the last topic, that is shielding the noise. You must have come across wires, and those wires have been shielded some kind of aluminum foil. Let's see, not exactly whether it is aluminum or some kind of alloy has been used to reduce the cost, but what actually that foil is. Now why we are doing these things? Even in the example, sometimes you have come across that there are number of wires, but they are individually can be seen individually, but sometimes they have been twisted with each other. Okay, only pair of wires have been twisted. Let's see why they are doing so. So let's start with, first of all, static noise. So it occurs when there is a electrical field that distorts the signal. Now when electrical fields distorts the signal, it means, suppose we have the wires, and very close to the wire there is a electric field or electromagnetic field source is there, EM source is there very near to the wires. Maybe there is a high tension wire is passing through your dish TV wires. So you can feel that whenever there is a power supply on and off, there is a momentary noise in your TV. Okay, so it means there is a noise which is static and it's permanently there till that source is very near to this wire. So that is a static noise, and it is always due to electrical fields which is very near to the wires. And how can we avoid it? We can mitigate such kind of noises using continuous foil around the wires, like here. So you have aluminium foil which is wrapped around throughout the length of the wire. Okay, so with the help of foil you can easily remove this kind of static noise. The next is magnetic noise. It came from AC motors, transformers, and whenever there is a flow of current in electric machines, there is a EM wave flows, and that there is a magnetic field around that particular device, that machine. So that magnetic interference gives you the noise, especially when we are measuring something. These kind of noise becomes very significant, so we need to take careful about these kind of noise, and this can be easily removed. Now please note down, when we are talking about electric field noise, it can be removed with the help of foil shield. When we have magnetic noise, we can remove this with the help of twisted pair. What is twisted pair? Here it is an example. So two wires taken together, they are twisted with each other, and that is how we are cancelling the flow of north and south through those two conductors, because wires are behaving like conductors in a magnetic field, and that is how by twisting those two conductors we are cancelling that magnetic field. Then we have common mode noise, which is very sensitive when we are connecting with the help of when we are connecting sensors to the signal conditioning circuit, and it is very important to know about operational amplifiers in this case. And usually we have instrumentation amplifier to remove common mode noise. We will discuss in the further slides or further lectures how to remove a common mode rejection ratio, how to remove common mode signal using instrumentation amplifier. Okay, we'll discuss later. So but if I see how grounding can help us, so if we use the grounding on both the sides for sensor as well as for the signal conditioning circuit, we can remove the common mode noise. The noise which is common to both the grounds can be eliminated with the common grounding. Then there is a crosstalk. Crosstalk happens when we have some kind of communication telemetry on the same signal where we are doing some measurement. So this happens due to standard power lines, okay, or pulsating DC. This is also important to know about pulsating DC. Pulsating DC means the signal is DC, that is its level is always positive, not going below the zero, but it is pulsating, increasing, decreasing, again increasing, decreasing, although its value remains above the zero, that is positive. So we call them pulse DC circuit. Okay, so pulsating DC or standard AC signal is able to produce some crosstalks between different wires. When the number of wires are coming into a single big conductor, then there is a chances of having crosstalks. So in that case, what we can do, we can individually shielded twisted pairs. So we have one pair here and second pair is this one, let's say this one and this one. In that case we have individual shields like this and this. So I can shield this one and this one individually. So that is the advantage of individual shields, so that it can remove all type of noise which we are coming across through the signal transmission. So these are the different shielding types what we have discussed right now. This is a foil shielding. Outside all the wires we have a foil, and advantage is it has the protection when the signal is more than 50 kilohertz. So for high frequencies always use foil type shielding. Another is we can cover the core conductor 100%. It is low cost because we are using very thin kind of a foil. Second is there is a braid shield. Braid shield is not a continuous foil, but it is a woven around with a different very thin wires have been woven like a sheet. Okay, it is a bit costlier, but it has some other advantages. It can even protect from EMI or radio frequency interference. And third one is multi shield, that is there are multiple levels of the same uh, shield what we are used earlier, braid shield one level, then there is a foil also. So we have combined foil as well as braid shield. Outside we have a braid shield, then we have a thin foil around the wires, and also once we are twisting again, then we have a foils on them. So it's a multi-level, but it is very costly. Although we have other advantages like ease of termination, physical strength also increases of those wires. So these are the reference I've used in these slides. You can go for more detail to these references. And that's all for today's session. Thank you so much for watching this video.